Uh, Good afternoon, everyone. Today we are going to see another mathematical term which you already know partially, the logarithms. But so let us start with some example. Let's say we want to calculate 2 raised to 4. It's a very simple thing, right? So how do you write this as a in a log format? Anyone can help me?
So we can write 4 log 2.
4 log 2.
No, sir, 2 is not the base. 2 is just in general.
Okay.
I did not think about the base part.
Okay. Let's forget about the base. 4 log 2, you are saying?
Yes, sir.
Okay. Something is missing. Where is 16 in this? See, actually, log of 16 is 4. Okay. And we have to take the base as 2. So this is how you write 2 raised to 4 into this form. Okay. So if I ask you to write okay, let's say I ask you to find out what is the value of x. What you will do here? Obviously, it is x equal to log of this 12914 and so on. Okay, but for the calculation purpose, this is very difficult, right? We find it difficult with these two numbers. Okay, but imagine again we are since this unit has started, we are talking about 100 digit 300 digit numbers. Okay, or 1024 bits or 2048 bits numbers. Okay, the prime numbers and all these things. When both the numbers are 100 digit or 300 digits, this calculation becomes so difficult. Okay, and we are going to use this kind of property of this calculation as it is difficult. That's why we are using it in the cryptography, so that our cryptographic algorithm becomes so powerful so that it cannot be hacked. So how do you generalize this as, let's say, p raised to I equal to q? If you have this equation, then you can write it as I equal to log of q to the base p. Okay, so you must understand how to represent any term in a log format. Okay, now this is a very simple thing. You might have studied long way back, uh, but this is what the just a brush up of logarithm. Okay, but this is not the one which we are going to study today. The one which we are studying today is discrete log. Okay, the discrete log is uh, a bit different than this type of log. Discrete log contains modulo operator. Okay, because we are working on modulo operators since long time, uh, and it is a part of modular arithmetic. Okay, so let us see the example. Let's say 3 raised to 4 mod 12. We have actually seen few example like this. Can someone tell me the answer to this?
Nine.
9. That's correct. Yeah. So this is the one. If I ask you, let's say another example, 26067 raised to 14 raised to I mod 29867. Okay, I'm sorry, it's not, if it is not visible. Yeah. So, and if I ask you what is the value of I, obviously that will not be easy, right? So we have to take the help of discrete log. Okay, first let us find out how to represent this uh, equation in a log format. So we write this as 4 equal to discrete log. Okay, now here the base is completely different. Okay, the base here is, there are two terms which are mentioned in the base. That is this one. So this item will be the first one, and the modular, whichever mod operator is the second one, and then you take the mod of the 9. Okay, so this is how the representation in a discrete log. Okay, for the modular operation. Okay, now how do we calculate I here? Okay, because here I value is 4, and this is the formula for I to calculate I. Okay, similarly, we will write this as I equal to discrete log of, can someone find out this one? Discrete log of 14. Okay, this has to be the first item. The second item will be the mod operator. Okay, mod value, whichever mod. So if here in mod 12 you are taking, so 12 is the second one. So this will be the second item of the log, which is a base, and this will be the, okay, so I is calculated as discrete log of 2607 to the base of 14 and 29867. Okay, so if you calculate it, I will be 12. Okay, so the actually the meaning here is, if you know, this logarithm is already quite tedious term to calculate. Okay, if we modify this log with a mod operation, okay, which is also called as discrete log, okay, uh, that will become more difficult to calculate, okay, and to find out these values. Okay, so let us try to formalize what is discrete log here. So if we write it as, can we write it, this as A, let's treat this as A, this is b raised to I mod m. Sorry, it was not in the screen. So I'm just trying to generalize these terms. Okay, I'm giving this as A, this as B, this as I, and this as M. Okay, so for that, in that case, I is equal to discrete log of B and M of A. Okay, so this is the what you can say, this is the discrete log definition. Okay, any doubts here, guys?
No doubt, sir.
So let us try to see another few examples here. Okay, if I ask you to calculate 2 raised to 5 mod 3, it is 32 mod 3, so that will be 3 tens of, and it will be 2.
It will be 2.
Yeah, correct. So if it is 4 raised to 4 mod 11, someone please keep the calculator ready so that we will solve these examples quite quickly. It will be 3. Okay, but if I ask you in the discrete log format, let's say if I give you the expression 8 is equal to 5 raised to I mod 30. Okay, how will you do the calculation? Because you don't know yet how the discrete log is calculated. You know what is the equation and how it is represented, but you don't know how to calculate this part, right? So what is the choice in front of you? Do a trial and error, right? Let us try to find out whether I for I equal to 0. Okay, that means 5 raised to 0 mod 13. What is that? 1. As simple as that. 5 raised to 0 is 1 mod 13. It will be 1. For I is equal to 1, 5 raised to 1 mod 13. What is this value?
So 5 raised to 2, it will come as 8.
5 raised to 2 mod 13. No, 5 raised to 2 is 25 mod 13 is 12.
Sorry, sir, my calculation mistake.
Sorry?
It's a calculation mistake, sir.
Okay, sorry. No problem. So what I mean to say is here we have to keep continuing till we get the mod value as 8. So this is a trial and error. What is this one? 125 mod 13, 13, 7, 8. This is giving mod 8. Mod value as 8. Isn't it? Do you have a calculator?
Yes, sir.
Yeah. So I hope this is correct. So I value is 3 here, right? But can someone please go ahead and do the further mod operations and give me the answers?
For 5 raised to 4, it's 1.
It's 1, okay. I'm interested in couple of more values. This is 5 raised to 11.
So the pattern is repeating. So it's
Sir,
1,
for
2,
5
3,
raised to 7, it is 8.
5 raised to 7 is 8. Pattern is
8,
repeating,
yes.
someone said. So 5, 12, 8. 5, again 5 raised to 8 should be 5, I guess. I'm sorry, 1, not 5. And this one is
Yes, sir. The
5 raised to 11, again should be 8. Okay, so how many I values you are getting? So you're getting multiple I values here. Okay, and here, if you're getting such multiple values of I, okay, you can't actually use the discrete log in cryptography if you're getting multiple values of I. Okay, otherwise, the the other party, if you decided to share this kind of equation uh, with the receiver, and receiver will try to find out the values of I, and it keeps hopping around the values, then it will never come to know what exactly which value to be used for the decryption. Okay, so this doesn't help at all. So in the discrete log, what we should do is we should find out such calculation where I is unique. Okay, so I is unique or distinctive. That has to be the condition for the discrete log. Okay, so what will be the condition here? And that condition is called as primitive root. Okay, is called as primitive root. Now, what is this primitive root? Definition of this primitive root is, let's say we have a is equal to what is. So I'm just rewriting this. Okay, so I'm just rewriting this, and we want the I as unique. I should be unique. So what we are doing here is we want to get a condition so that I gets unique. Okay, only if B is a primitive root of modulo n. Okay, this is the condition we are adding. Okay, so what is this condition means? First of all, let us try to find out what is primitive root means and when you find out what is primitive root, then it satisfies this condition that I can be unique for this one. Okay, so let us try to find out how the primitive root is calculated. Okay, so what I'll do, what we have to do here is, let us try b values here: 0, 1, 2, 3, 4, 5, 6, and so on. Okay, and in the column, what you do is you put a b raised to 0, b raised to 1, b raised to 2, and so on. Okay, and in the cell value, what we are doing here is we should write it as b raised to I mod m. Okay, these are m minus 1, b raised to m minus 1. Okay, so we have to calculate this kind of table. And what is that table? Can you tell me the first value here? So if the b's value is 0, what we do is it raised to 0 mod m. Okay, let us consider m value as 13. Am I audible properly?
Yes, sir.
Okay, so what we have to do is we have to calculate this part and put it in the cell value. So here it will be 0, 0 mod 13 will be 0, and this will be all zeros, because 0 raised to 1, 0, 0 raised to 2, and so on. So let us try with 1. 1 raised to 0 mod 13. It will be 1. 1 raised to 1, I'm sorry, this will be 0. This will be 1. Okay. Then 1 raised to 2 mod 13. Again, it will be 1, and so on. So all the values will be 1 till b raised to 12 here. In this case, b raised to 12. Okay. For 2, b raised to 0. Let us forget about this. B raised to 1. 2 mod 13. It will be 2. Okay. 2 raised to 2 mod 13. It will be 4.
4.
If you're not understanding, please let me know. 2 raised to 3 mod 13. What will be the value?
So 8.
8. 2 raised to 5. I'm sorry, 2 raised to 4.
3.
Okay. Next one, 2 raised to 5. 2 raised to 5. We can't ignore this one. 2 raised to 0.
So 6.
So it will be 6. 2 raised to 6. 7, 8, 9, 10, 11. It's too much.
Two raised to 6 mod 13 will be 12.
Okay. I don't know. I'm just believing you. Just give me the values. let me just pull out one Excel sheet that I have prepared. Okay, so writing up Excel sheet is here. We don't have to calculate. So let us say M value is 13. This will have to be okay. Now I hope this is correct. 15 raised to 1 mod M. Can someone check these values if you're getting the same 12?
Sir, for 2 raised to 4, it should be 3 instead of 6.
It should be 3. Okay, why it is? Okay.
Because 2 raised to 4 is 16, so
Right.
3.
So I think I have made a mistake here. I'm sorry. 2 raised to 4. Right.
So for 2 raised to 5, I mean that 2 part, it should be 6.
I'm sorry, I made a mistake. I didn't prepare a proper Excel sheet. 6, 7. This should be 8. I'm sorry, guys. This should be 9. This should be 10. So, okay, is it correct now? Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. Okay. So let us forget this row and this row. Okay. Right. So what you'll have to do is for finding out the primitive root, we have to get this table going. Okay. So here, the B value B values are the row values from 1 to m minus 1. Okay, and then we have the value of m modulo m. Okay, we have the modulo m, and then we have prepared this table. Okay, if you observe this table, for any row which let's say for 1 the values are getting repeated. Okay, for 2, is there any value getting repeated?
No, so no value
There
is
is no
repeated.
value is correct. There is no value getting repeated here, right? For 3, the series is getting repeated here. 391, 391, 391, and so on. For this one, 4, it is getting repeated. 4, 3, 12, 9, 10, 4, 3, 12, 9, 10, 1. Right. The values are getting repeated. 5, also it is getting repeated. For 6, it is not getting repeated.
Yes, so no values are repeated.
Right, correct. So let's find out those rows where no values are getting repeated. I guess 7 also is there. Please tell me if I'm wrong. Repeated, 9 is repeated, 10 is repeated, 11 is not repeated. And this is repeated. Okay. So what you'll have to do here is you have 4 values of B. That is 2. The next one is 6, 7, and 11. So let us go back to the sheet. So B values are 2, 6, 7, and 11. Okay. So if you do the operation B raised to I mod 13, okay, or 6 raised to I mod 13, or 7 raised to I mod 13, or 11 raised to I mod 13. If you do all these operations, okay, for all these operations, I will be unique, as we have just checked. These are I values. Okay, I values will be completely unique. Okay. And what is I value here? I is D log B and M, 2 raised 2 and M and A. Now, A here will be different. Okay. Okay, it can be any value here. But the condition that we have just written as if B is primitive root of M, then and then only you can have a unique value of I. So this is the condition. So 2 and 13 are primitive root of each other. 6 and 13 are primitive root of each other. 7 and 13, 11 and 13 are primitive root of each other. So when you get these conditions, when you get the two numbers as primitive root of each other, so if these two B and M are primitive root of each other, then and then only I will be unique. Okay, and then you can find out the discrete log of the whole value. Okay, this is the condition here, right? So what you can do is you can actually prepare the table whenever the question is asked about the discrete log, how to find the discrete log. First, you have to check whether the primitive root is possible. Okay, so if I give you the example, another example, instead of 13, let's put it at 11. Okay, so this will not be there because this has to be b raised to m minus 1. Okay, in that case, we'll delete this. We will delete this. Okay, and we'll try to. Okay, can you please tell me now which are the primitive roots of 11?
So 2,
Okay, 2,
6 and 7.
again the same thing.
Yes, sir.
Okay. Eleven and 13 are prime numbers, right? So can
So
we?
even 8 might be the primitive root.
Yeah, 8 is also a primitive root. Yes, it is. Right. So if the m value is changed, I was just worried that how it is possible because we got the same answers. So for 11, m is 11. We are getting the 2, 6, 7, and 8 are primitive root of 11. Okay. We should also consider this value with the set like this. Okay, so you got the point here, what is primitive root and how the primitive root is helpful for finding out the discrete log. Okay, and we are actually working with the single digits and very small digits here. Okay, but believe me, these are all 300 digit numbers when get into the business of cryptography. Okay, so that is one topic which was remaining, discrete log. If you have understood what I want to do is, I hope the problem is readable. Find the smallest multiple of 10 which has a remainder 1 when divided by 3, remainder 6 when divided by 7, and remainder 6 when divided by 11. Can you find out this number? We have seen multiple things here. First, we have seen modular arithmetic. I'm sorry, this is not uh, visible for you, whatever I'm writing, modular arithmetic. Then we have seen Euclidean algorithm. Then we have seen extended Euclidean algorithm. Can someone please tell me what are the things we have studied here? Euler's phi function. Then we have seen RSA. Then we have seen multiplicative inverse. Then we have seen Chinese remainder theorem. Then we have seen this one, primitive roots and discrete log. Okay, there are a couple of more items in the maths which are pending. But to solve this example, what are the things you should know? Or what are the things you will use from the list? First, try to understand the problem. If you have understood the problem, tell me which are the terminologies you will use.
So we need a unique answer for all. Maybe primitive root could be useful.
Okay. Why do you need primitive root here?
So the question also says that it gets this particular remainder when divided by a particular number, and it is different for all. So maybe like for each, it's having a unique. So जहाँ पे भी वो unique आ रहा है, maybe that could help in finding the smallest multiple of 10.
Okay. Anything else that you will require? By the way, this was the problem asked a couple of years back in the exam. So you'll have to use multiple terminologies here, but it is related to one particular term.
And multiplicative inverse could also be used. I'm
Multiplicative
not sure though.
Okay, I'll take that. Anything else? So it's a very simple thing. See, can I write this as has the remainder 1 when divided by 3? That means what? 1 mod 3. Sorry, this one. 1 mod 3. Okay. So I'm just considering the first statement, which has the remainder 1 when divided by 3. Okay, which has the remainder 6 divided by 7. So 6 mod 7. Next one, remainder 6 when divided by 11. So that means what? 6 mod 11. Okay, so and we have to find out the smallest one, smallest multiple of 10. That means actually 10x, we can say. We want to find out x, which is a multiple of 10. Okay, forget about 10. So in this case, if you remember any terminologies where we have solved this kind of problem.
Extended Euclid's algorithm.
Extended Euclidean algorithm. Okay, we'll take that.
So can we use Chinese remainder?
Yeah, that was the one I was looking for, because we have solved the example, this kind of examples in Chinese remainder theorem. Okay, where this is A1, A2, A3, and this is N1, N2, N3. And we have done a lot of calculations there, where multiplicative inverse is used, extended Euclidean algorithm is used, and Euclidean algorithm is also used. Okay, but finally you have calculated CRT, and CRT is used to find out the value of x here in these equations. Okay, so guys, what I want from you is, whatever we are learning through these mathematical terms, please try to understand it very well, because in the exams, these things will come in different way. You should relate whatever the problem is asked, kind of problems. You should relate that problem with what we have learned up till now. Okay, so one more thing is remaining, that is secret sharing. And digital signature. Okay, maybe it will be finishing. It will finish in one lecture or maybe 2 lectures. So by this week we will be finishing unit 2, definitely, and maybe next week we can think of starting unit 3rd. Okay, and or we can just take a revision of first 2 units, depending on your inputs. We'll do that. So here I'm just